Hello everyone. Today my group, Group 3, Section 4, Engineering Mathematics, would like to present you all a topic on Newton's law of cooling and growth and decay. Firstly, I would like to introduce the group members in my group. The first one is Daniel Kaujunze. Second one, Syam Sundar anak Kari Sriram. The third one is Yap Zong Lee. And the fourth one is Dharineshwaran anak laki Divakar. Before continuing our presentation, we would like to thank all the individuals who supported and guided us. Special thanks to Puan Dr. Nur Haliza binti Abu Bakar, all the group members, UTHM, and our classmates, friends, and families for the encouragement and moral support. Thank you so much.
This is Villa Table Part A.
My name is Daniel Kaujunze, so I'm going to talk about the content part. In Part A, we have successfully derived the formula T equal to TE plus TO minus TE e power of negative KT. First, we apply dt over dt equal to negative K T minus TE, where the TE is the environment temperature and the K is constants. After that, we move the dt to the right and the T minus TE to the left. Then we integrate the left side and the right side. We'll get ln T minus TE equal to negative KT plus C. After that, we make it become T minus TE equal to e power of negative KT plus C, which equal to e power of negative KT times e power of C. Since C, e power of C is a constant, so we make it to A. So we get T minus TE equal to A e power of negative KT. So we can simplify as T equal to TE plus A e power of negative KT. To find the value of A, we will sub T equal to 0 into the equation. So we'll get T equal to TE plus A times 1. So we know that A is equal to T0 minus TE. So the final formula will get T equal to TE plus TO minus TE e power of negative KT.
Alright, just took the cake out of the oven. It's super hot, about 300 degrees Fahrenheit. I'll let it cool down. How long until the cake cools down to 85 degrees Fahrenheit? And what will its temperature be after 1 hour?
Hi, Syam. Yeah, I got errands to run a while, so I'll be back by 1 hour. So when I balik, we eat the cake together, can? Yeah. Thank you. Bye.
No!
Now, I'll be explaining for the solution for part A. So for this question, there are two parts, 3A and 3B. So let's start with 3A first. The formula that I'll be using is T equals to TE plus bracket TO minus 3E closing bracket multiply with E to the power of KT. So after reading this question, we know that TE is 70 Fahrenheit, which is the temperature of the surrounding, and T is equals to 3 and T3 is equals to 200. This is because it's the temperature of the cake after 3 minutes, and TO is 300 Fahrenheit. This is the temperature of the cake initially. So the main goal of this question for 3A is we have to find the time needed for the cake to cool off to 85 Fahrenheit. So in order to solve this question, we first have to find the value of K. So firstly, from the given time T is equals to 3, 200 equals to 70 plus 300 minus 70 multiply with E to the power of negative K. We will be putting T as 3. So we can write this as 200 to 70 plus 230 multiply with E to the power of negative 3K. So we just have to bring equation properly, and we can get 200 minus 70 equals to 230 multiplied with e to the power of negative 3k, and we can get 130 equals to 230 multiplied with e to the power of negative 3k. So after this, we have to know that we have to remove the e, and in order to do that, we have to add in ln. So before doing that, we can bring 230 this side, which brings us up to 130. Well, 230 is negative 0.5705, and k will become 0.1902. Now, after finding k 0.1902, now we just have to use the formula back again, which is T equals to Te plus To minus Te multiplied with E. So since we have to find the temperature at 85, so T will now become 85, hence 85 is equals to 70 plus initial temperature 300 minus 70 of the surrounding temperature multiplied with E and the constant K 0.1902 and T. In order for us to remove the E, we have to add in a ln, which brings us up to 0. So 15 over 230. Now we just have to add in the ln, and we will get negative 2.73 and 0.1902T, which brings T up to 14.35 minutes. So this will be the answer for part 3A. Now I'll be explaining for part A, solution, question 3B. So for this question, the goal for us is to know the final temperature of the cake after an hour. So this shows that T for us this time will become 60. So we will be getting 70 plus 230 E and to the power of negative 11.412. So from this we will be getting 70 plus 230 multiplied with E to the power of negative 11.412. Then we'll be getting 70 plus 230 bracket 1.106 multiplied with 10 to the power of negative 5. Finally, 70 plus 2.544 multiplied with 10 to the power of negative 3, and we will finally be getting T for an hour, which is 70.003 Fahrenheit. So this will be our answer for the final temperature of the cake after 1 hour.
This is Villa table part B. dn over dt equals to negative Rn, dn equals to negative Rn dt, n to the power of negative 1 dn equals to negative R dt, integrate n to the power of negative 1 dn equals to integrate negative R dt, ln n equals to negative RT plus C, n equals to e to the power of negative RT plus C equals to e to the power of negative RT times e to the power of C. EC is a constant. We make the constant into A. NT equals to AE to the power of negative RT. Let T equals to 0. N0 equals to AE to the power of negative K times 0. N0 equals to A. Sub A equals to N0. NT equals to N0 N0E to the power of negative RT.
I took the medicine about 12 hours ago. My body still feels weak. Why do I still feel sick? Is the medicine still in my system or not?
Now for part B question. Hydrocodone bitartrate is used as a cough suppressant. After the drug is fully absorbed, the quantity of drug in the body decreases at a rate proportional to its quantity left in the body. After 3.8 hours, the amount of hydrocodone bitartrate left in the body is half of the original dose.
which is usually about 10 milligrams. What is the amount left after 12 hours? So the goal of this question is to find the amount of hydrocodone by tartrate after leaving for 12 hours by applying NT equals to N naught multiplied by the exponential with power negative RT to get the answer. Now, from the question, we know that when T equals to 3.8, NT, which is the quantity, is equal to half of the original, which is 10. From here, we know that NT equals to N naught 10 times exponential E. R is the constant and T is 3.8, which is 5 equals to 10 E 3.8 R. Now, bring the 10 over, we can get ln both sides, which is ln half equals to 3.8 R. From here, we can get that the value of R is equals to 0.1824. Now, we want to know how much quantity that is left after 12 hours, which is T equals 12. When T equals 12, N 12 equals to initial number, which is 10 E negative R 0.1824 multiplied by 12, which is we get the value 10 times 0.1121, which is equal to 1.121 milligram, which is the answer. So, first, we need to find the value of R by using the formula, the normal formula. When T equals to 3.8, it is the half of the quantity, and after that we found the value of R, we substitute into N12 and we get the final answer.
Conclusion. Overview of the report. Explored mathematical models related to Newton's law of cooling and exponential decay, focused on real-life application like temperature changes and drug decay, hydrocodone by tartrate. Problem solving and application. Applied relevant formulas to solve real-world problems. Observed how these models accurately predict changes over time. Reinforced the role of mathematics in modeling physical process and making predictions. Mathematical derivation. Learned how the formulas are derived from the first principle using differentiation and integration. Gained deeper understanding of how real-world behavior is translated into mathematical equations. Overall learning outcome. Improved our problem-solving skills. Gained insight into the practical use of engineering mathematics in real-world scenarios. Recognized the importance of differential equation in various fields of engineering and science.